Today we are going to cover 13.1 Introduction to Limits. So going to copy the essential question, how do you find the limit of a function for a certain value of x? Go ahead and paste your cutout or copy it down and pause it. Once you're ready, we can start. So the definition of a limit. If f of x becomes arbitrarily close to a unique number L as x approaches a from either side, and that is the key thing. As x approaches a from either side, if f of x approaches the same value, L, then we say that L is the limit. This is the notation, and is read the limit of f of x, as x approaches a from the left and from the right. The limit is L. So therefore, we are going to approach from the left and from the right. And we're going to go over this concept in three different manners. We're going to use a table to find the limit. Then on example number 4, we're going to use direct substitution. And finally, on example number 5, we are going to be using graphing in order to be able to find the limit. And hopefully that will make a little more sense as we find the limit as x approaches a from both sides, from the left and from the right. We're first going to use a table to estimate numerically the limit of 2 of x minus 3 as x approaches 4. So notice that the little arrow means approaches. So we want to be able to find out as x approaches 4 from the left and from the right, what will be the value of this function. So first we're going to make a table, and we're going to make a horizontal table in this case. So you can use a ruler or your ID. And we're going to plug in values for x. And we're going to end up with values of y or f of x in this case. And I want to be able to find values that are close to 4 from the left. So closer to 4 from the left, so smaller than 4 will be 3.9. And let me use 3 squares for this case. And I'm going to use a calculator. So in this case, I'm just going to plug in a 2.9, a 3.9. So 2 times 3.9 minus 3. That gives me 4.8. So therefore, the y value for the graph will be 4.8. Well, I want to get closer to 4. So therefore, I'm going to use 3.99. Still on the left of 4. So therefore, I'm going to type in 2 times 3.99 minus 3. That gives me 4.98. I want to get closer to 4. So therefore, I use 3.999. So I'm going to type in 2 times 3.999. And if you have a graphing calculator, you can use Desmo's calculator, scientific calculator, that works pretty well, or any other scientific calculator that you have, minus 3. That gives me 4.998. In here, I'm going to leave a space to be able to plug in a, let's say, 4. Now, I want to be able to go over to the other side. So what's the number? And let me just go 1, 2, 3. So I'll go 3 spots to the right. 1, 2, 3. So therefore, I'm going to use 4.1. And I'm going to type into the calculator. 2 times 4.1 minus 3 will give me 5.2. I want a number closer to 4. So I'm going to use, correct, 4.01. It's going to get very, very close to 4. So therefore, will be 2 times 4.01 minus 3 will give me 5.02. And I'm going to get closer to 4. So this is not close enough, so therefore I'm going to plug in 4.001. And that's as close as we're going to get. Therefore gives me 5.002. Notice that from the left, this number is getting closer and closer to 5. And from the right, this number is getting closer and closer to 5 as well. So therefore we can say that the limit of 2x minus 3 as x approaches 4 is equal to 5, because it approaches it from the right and approaches it from the left. Now if we actually take the time to graph it, so let's go and graph this on decimals. We have 2x minus 3. And I want to be able to find out, and this will be f of x equals. And I want to be able to find out what happens to the graph as x gets closer and closer to 4. So therefore, let me place a vertical line at x equal to 4. So as we get closer and closer to 4, the x value, notice that in this case, the x value is 2.1, 2.2, 2.7, 2.9, 3.1. What's happening to the y value? The y value is getting closer and closer to 5, correct? From the left. And from the right is just that. But this is just using a table. We can confirm that from the left it approaches 5, from the right it approaches 5. Let's go to example number 2. On example number 2, we are going to use a table once again. So go and copy it down, and we'll continue once you are ready. Go and pause it. So in this case, you might think, well, hold on this. Can I just do the following? Can I just plug in a 4? 2 times 4 is 8, minus 3 is 5. Yeah, that works. But in this case, we need to make a table. We'll use direct substitution on example number 4. So therefore, you might want to say, well, can I do the same thing for this one? If I plug in a 1, notice if I plug in a 1, 1 minus 1 gives me 0. So therefore, your denominator is 0. That means it's undefined. So that's why using the table can be very useful when you find in the limits. So let's use a table. We are going to make a horizontal table of values. I'm going to plug in values for x. That will give me back values for y, for f of x. And I want to be able to find the limit as x approaches 1. So therefore, I'm going to approach 1 from the left and from the right. So what's the number less than 1? Correct. That'll be 0.9. And I'm going to use my calculator to plug it in. So therefore, I'll use my fraction. I'm going to press my alpha y, and I'll use the fraction bar. So therefore, I'm going to plug in 0.9 to the power of 3 minus 0.9 square plus 0.9 minus 1 over 0.9 minus 1. So that looks correct. So therefore, I end up with 1.81. Now, I want to get closer to 1, so therefore I'm going to plug in 0.99. Correct. So therefore, let me just go second entry, and then I can go back. If you have a cancel, you can just move up and retype it. And when I type this up, I'll just click on insert. Second insert in 9. Second insert in 9. Second insert in 9. So therefore that gives me 1.9801. I want to get closer to 1. So I'm going to use 0.999. And there's other ways that you can actually evaluate on the graphing calculus, but for now I'm just going to use the old-fashioned method of insert or replacing the numbers. Or you can retype it if you want. So therefore that gives me 1.998. So therefore this is approaching, you can see this approaching 2, correct? So let's see what happens on the right. Once again, I'm going to use 1, 2, and 3. And one number should plug in starting at 1.1. Then it will be 1.01 and 1.001. So let me just go back or re-entry. Just make sure that you do it carefully. Forgot parentheses in there. So therefore, that gives me 2.21. Let me type in 0.1. So let me insert a 0 in there. Make sure I do it in the right location. Looks good. So therefore, that gives me 2.02. And once again, I'm going to type in one more. And as you guys can see, it is getting closer and closer to 2 as well. And we'll look at the graph right now. We graphed this type of functions, rational, back on chapter 4, I believe. And therefore, it gets closer and closer to 2.002. So therefore, from the left, it also approaches 2. So therefore, we can say that the limit is 2. Do you guys remember what type of graph this is? Correct. So in this case, this is a rational function. So I type in x. I make my fraction right away. You can also use your table, and then you have a fraction division in there. And do they have a function? No. So just by doing the divide by, it will give you the fraction. Now another way that if you want to be able to evaluate this, you can also just say f of 1.01. It does it for you here. So if you want to do decimals, it's a little easier. For purposes today, I'm just going to use a calculator. So therefore, this looks like a parabola. Do you guys realize? Do you guys remember why this looks like a parabola? Because you can actually factor this out. You can factor the x minus 1 out of here, and the x minus 1 cancels out. So therefore, there should be a little hole at 2. At 1, a positive 1. So notice that in this case, let me give it my keyboard. If I go through, I can see that there's. So we covered this type of graphs back in chapter 4 or chapter 5. So therefore, as we go from the left, the y value gets closer and closer as x approaches 1. The y value gets closer and closer to 2. But does it ever reach 2? No, it becomes undefined. And from the left, it also approaches 2. So even though there's no value at 1, the limit still 2 because it approaches the same value from the left and from the right. Example number 3. Go and copy it down. We're going to once again use a table to estimate the limit. Go and pause it. Excellent. So do you guys remember what type of function is this? This is a piecewise function. So basically we have two pieces of a function that together this will make a function. This is the domain. So therefore the 2x plus 1 will apply when x is less than or equal to 3. The 4x minus 5 will apply when x is greater than 3. But first let's go make a table of values. I'm going to plug in values for x. That will give me back values for y or f of x. And I want the limit as x approaches 3. So notice a different way of writing it down. So this could be one way of writing it down. Sometimes they'll tell you that the limit as x approaches 3 of f of x, and they give you the function separately. So therefore, I want to be able to find values closer to 3 from the left. So we are going to use 2.9. Now 2.9, will that be applied to the first domain, to the first piece, or to the second piece? That will apply to the first one. So therefore I'm going to plug in 2.9 on the first part of the function, on the first piece of the function, plus 1. So that gives me 6.8. Now I'm going to plug in a number closer to 3, so I'm going to use 2.99. Excellent choice. That gives me 6.98. I need to be able to find a number closer to 3, so I'm going to use 2.999. So we 2 times 2.999 plus 1. That gives me 6.998. Then this will be 3. I want to be able to find numbers coming from the left. So which number should I start with? Correct, it should be 3.1, then 3.01, then 3.001. Now 3.1 applies to the second domain. So in this case, this first 3 numbers applies to the first piece of the function. This numbers on the right apply to the second piece. How about the 3? The 3 applies to the first or the second? Correct. That's part of the first function. So therefore I'm going to plug in 4 times 3.1 minus 5 will give me 7.4. Notice that in this case, this one was approaching 7. And this one looks to be approaching the same. So before times 3.01 minus 5, that'll be 7.04. And 4 times 3.001 minus 5 is 7.004. So therefore on this side it's going to approach 7. It approaches 7 from both sides. So therefore we said that the limit as x approaches 3 of f of x is equal to 7. And notice that sometimes you might think, well, can I just plug in a 3? Sure, but that's not always going to work on this piecewise functions, where we have to be careful. We can use substitution And if we know the graph, we know that's continuous, and we know where the breaks are, then we can use direct substitution to be able to find the limit. Such as example number 4. Well, actually, let me go back to example number 3. Let's do it graphically, because that's not something I did. So because we need to also practice, how can we type in the function in decimal? So f of x equals will be 2x plus 1. Now, to be able to take care of the domain, do you guys remember how to do that on decimals? So we're going to place a brace, automatically will close it for us. So the x is less than or equal to 3. And f of x equals 4x minus 5 when x is greater than 3. And notice that automatically closes it for us. And this is the graph. Let me bring it down. So therefore on the left, it's approaching 7. And from the right, or from the left, approaching 7. And from the right, approaching 7 as well. So therefore, if you are able to see it graphically, you are able to see that it approaches 7 from both sides. Example number 4. Let's do it direct substitution. When pause if you need more time to copy it down. So let's use direct substitution. Now remember that you can only use direct substitution if you know what the graph looks like. Do you guys know what the graph looks like for this one? This is correct. This is a problem. Are there any gaps in there? Are there any vertical asymptotes? No, this is just a continuous graph. So therefore we know that the limit is going to apply anywhere, and we can just plug it in. So therefore, if we know what the graph looks like, and we know where the gaps are located, then we can determine if there's a gap at -1 on the x value. In this case, we know that there are no gaps, so we can just plug in a -1. And I'll plug in a -1 instead of each of the x's. That gives me 1 plus -1 minus 6. So it gives me 0 minus 6 is -6. So therefore, the limit as x approaches -1 of f of x is equal to -6. So, and if we actually take the time to graph it, f of x equals x to the power of 2 plus x minus 6 when x is -1. Let me just bring it up. My computer gets a little warm after a while. Use substitutions to see what you get. But before, let's discuss this. Before you actually work it out. We know, what does the graph looks like in this case? Well, we know that it's a rational expression, and we know that there's going to be a gap at -3, correct? Correct. And what should the graph look like? Can I have an idea? Excellent. So let's just plug in a -1, and we'll talk about the graph in a second. So we have -1, and there should be an equal sign in here. We have x squared plus x minus 6 over, and I want to plug in a -1. So therefore, f of -1 equals, this is 1, 0, gives me -6, divided by 3. F of -1 is -2. So therefore, the limit as x approaches -1 of f of x is equal to -2. Remember that the gap in here was a -3. So we know that there was no gap at -1. So therefore, we were able to just use substitution. And if we actually take the time to graph it, we're going to use f of x equals, Well, I use my fraction right away. To the power of 2 plus x minus 6, x plus 3. Correct. This is a line. And remember that if actually take the time to simplify x and x, 3 and 1 positive and 1 negative, no, 3 and 2. That gives me x squared minus 2 plus 3x is positive x minus 6. My x plus 3 cancels out. So therefore, x minus 2 will be my graph. But we do have a graph, a hole when x equal to negative 3. So even though that it seems like it's right there, correct? That's undefined. Example number 5. Go and glue your cutout or copy it down. Copy example number 5. And in this case, we're going to use decimals to be able to find the limit. Go and pause it if you need more time. So there's some conditions under which the limit of a function as x approaches a specific number fails to exist. Let's go and go through each one and then we'll come back to this. Find each limit by graphing the function. So let's use decimals to graph the first one, then we'll just copy it down from decimals, or you can use your graphing calculator as well. So in this case, we have f of x equals 4x minus 5, within the domain of x is less than or equal to 2. F of x equals 3x minus 5, with the domain of x is greater than 2. So notice that in this case, as x, we want the limit as x approaches 2. So let me just plug in x equal to 2. So we can see it. Let me place it in red. So notice that as x approaches 2 from the left, is getting closer and closer to 3. But as you get closer and closer to 2 from the left, it's getting closer and closer to 1. So therefore, there's no limit. The limit does not exist. So let's go and copy it down. So we'll make it 5 by 5, and on your homework you do need to copy it down to 4, 5. That's a very quick graph, it's fine. Negative 5 for both, positive 4, and as x is greater than 2, you can just copy directly from, and add 3 to the right 1, add 3 to the right 1, 3 to the right 1. So therefore I need this part. So therefore, this one's closed and this one's open. Limit does not exist. And in this case, that will be your first case. F of x approaches a number L, which in this case will be 3, as x approaches from the left, and approaches a different number M, which is 1, as x approaches 8 from the right, as x approaches 2 from the right. So this will be case 1. Letter B. Go ahead and graph it. Let's graph it together. We have the first function, f of x, x equals x minus 1. The domain is x is less than 3 for this piece. F of x equal to 4. The domain is x equal to 3. So notice that in this case, it's supposed to be a horizontal line, but we just have a point. So decimal doesn't show for us, so we'll graph it in a different way so we can see it. When x is greater than 2. So, and that should be a 3. We want it to be. So therefore, this, the one in red that's not showing through, we're just going to graph it that x value is 3, the y value is 4. And I'll just place it as red so we can see that it's the same. So therefore, on the left, from the right, f of x is approaching 2. So even though there's a point above, the gap at 3, you get 4. From the left, you're approaching 2. From the right, you're approaching 2. So therefore, the limit is 2. Go and copy it down on your paper. I'm going to do it pretty quickly. And this is open, and in this case, that's 4. So therefore, this limit does exist. The limit as x approaches 3, or the function, is positive 2. So notice the difference between those two piecewise functions. Example C and D. Go and copy it down. We're going to do it by graphing once again. Go and pause if you need more time to copy it down. I'm going to make a graph, so I'm going to make a 5 by 5 for each one. So the question is, do you know what the graph on the left looks like? So we covered this type of graph is a rational expression. So therefore, when I graph it, we get rid of all these graphs. F of x equals 1 over x to the power of 2. It looks something like this. If I go from the left, as x approaches 0, so I want it to approach 0. The limit is 1. So notice that in this case, the value as x approaches 0, the value of y is infinity from the left and from the right. This does not qualify for a limit. Let me just make a very quick graph. If we plug in a -1, gives you 1. So therefore, the graph looks something like this. And same thing here. Plug in a +1 gives you 1 as well. So in this case, whenever the limit approaches positive infinity, there's no such limit because we never reach infinity. So therefore, limit does not exist. If by any chance you have a function such as just 1 over x, the limit will not exist as x approaches 0. Because this one going to negative infinity, this is going to positive infinity. Now, if this was the same function, but as if it was the limit as x approaches +1, then yes, there's a limit as x approaches +1, because in this case, they both are approaching the same point. But if x is approaching 0, there's no such limit. And the last one is 1 over the sine So the question is, do you guys know what this graph looks like? No, this is actually a very interesting graph, 1 over x. That is the graph. And in this case, this is what we call no such limit in this case. And it goes all the way up to 1 and all the way up to -1. Therefore, it goes. Notice that in this case, let's get this point here. This point is -0.6. So therefore, it goes up to here and up to here. So this graph comes from here. It comes down, and then it starts to go up and down, up and down. And on this side, it comes the same way. And it goes. So there's no such limit. Limit does not exist. So in this case, this will be case 3. And this will be case 2. So that is the notes for an introduction to limits. Email me if you have any questions, and have a great day.